Welcome back. This unit will be talking about when is it the case that two propositions are logically equivalent to one another. Okay, so suppose that I have propositional formulas A and B. These are said to be equivalent, sometimes semantically equivalent or logically equivalent, if it's the case that they have exactly the same truth value for all assignments. That is, they have the same truth table. Okay, one notational point here. Note that we denote this equivalence by the equal sign with 3 lines on it right here. Okay, so let's see some examples. Is the proposition P implies Q equivalent to not P or Q? Okay, remember, if you recall from the previous unit, we talked a little bit about this with some of these strange examples for when implications evaluate to true. Okay, so how can I give you the answer to this? Well, one way to prove either equivalence or non-equivalence is just by showing the truth tables. Okay, so I've already filled in for you here the truth table of P implies Q. Now the next step is, how do you go through and compute the truth table of not P or Q? And for these things, I recommend that you write them out in steps. Here I have separate columns along the way. So the first thing, for example, would be to evaluate not P on its own. Then you can take the Q column, the not P column, you can order them in your mind, and you can fill out the final column. Okay, so now what do I see? I see 2 columns for the 2 propositions that are identical. This means these propositions are equivalent. Okay, how about another one? Suppose I take P implies Q, and now I'm looking at not Q implies not P. Looks a little goofy. Okay, so same game. Here's the truth table for P implies Q. Let's break this second part into steps again. Not Q, not P, and now the implication between those two. So remember, here you kind of go through line by line and see when is it the case that the first part is true, the second part is false, and that's the case when you'll get a false for the implication. Okay, so taking a step back, we see again these columns are identical, which means that these 2 propositions are also equivalent. So now this thing looks a little strange. Not Q implies not P. And note there's 2 things, so I flipped the order and I negated both of them. This might look a little odd, but this is actually something that comes up a lot. So much so that it gets a name of its own. This is called the contrapositive of P implies Q. Okay, so here this is rewritten up here, and let's take a look at some examples. Okay, suppose I say, if it rains, then it is wet outside. Okay, so what are my P and Q? Here P is it rains, Q is it is wet outside. So what is the contrapositive? I need to flip the order and negate both of them. This gives me, if it is not wet outside, then it did not rain. Okay, so now check yourself, think about this. If it rains, then it's wet outside. So suppose I go outside and it's not wet. What does that mean? There's one thing that you know, it must not have rained. Okay, so this is kind of an intuition for it. And always, it will always be the case that an implication is equivalent to its contrapositive. Okay, so this one, again, I flip the order and I negate. This one stays equivalent. What if I just flip the order? This is known as the converse of P implies Q. Here we have Q implies P. Is it the case that the converse is equivalent? Okay, so let's take a look. Again, if it rains, then it's wet outside. Is it the case that if it's wet outside, then it must have rained? This case, not necessarily. Okay, for example, maybe there was a sprinkler, maybe there was a bucket, who knows, okay? But it's not necessarily true that it has to have rained, versus the other case where there was no other option. It had to be that if it was dry outside, it could not have rained. Okay, so here I'm saying that a converse is not equivalent to an implication. That is, P implies Q is not equivalent to Q implies P. And to see that, mathematically, take a look at their truth tables, and you'll see that they have a false in different rows. Okay, so indeed, these are not logically equivalent. Okay, so keep in mind the contrapositive and the converse. These will come up on and off throughout the semester. I also want to give a few other useful examples of logical equivalences. The first, which we'll see in just a second, are known as De Morgan's laws. And the second collection are distributive laws. Okay, so De Morgan's laws, named after De Morgan, are ways of taking a negation to either an and or an or. Okay, so let's take a look at the first one. The first statement is that not P or Q is equivalent to not P and not Q. Okay, so first of all, think about an example to try to get some intuition. Suppose I say that I am not short or Brazilian, okay? That means that I am both not short and I'm also not Brazilian. Okay, so good, that checks out. But perhaps more rigorously, in fact, we know that proof by example is not a thing. Here you can see that these are indeed equivalent. In fact, both of them evaluate to false unless both the inputs are false. Okay, and in a similar light, so this was a negation of an or. There's a similar rule for a negation of an and. Okay, so if I am not, okay, maybe too much creative here. I am not Brazilian and American, that means I'm either not Brazilian or I am not American. Okay. So this one I didn't draw the truth table, but it's a good idea actually to kind of go through as an exercise and do it yourself. Okay, but what's the punchline of this slide? If I have a negation of an and or an or, what happens? I need to kind of distribute the negation in and flip whatever the and or was. Okay, so don't forget about that part. Okay, the last part for this mini session will be this last example of logical equivalences for distributive law. So before I had negation of an and, now suppose I have mixes of ands and ors. Okay, so for example, this first one, P and Q or R is equivalent to P and Q or P and R. Okay, so come up with I'll leave the creativity to you for this time, but try to come up with some examples of P and Q and R and convince yourself that this makes sense logically. And what I'm going to do is I'm going to prove it for you via truth tables. Okay, so let's go ahead and prove this first one. And I'll do this by showing the truth table of both sides and showing that they're the same. Okay, so now take a look. You'll notice that my truth table is taller than it was before. This is because you need to, recall, have a row in the truth table for each one of the possible choices of true, false for all the inputs. Okay, so for example, if my proposition had one input, then I had 2 rows. If I had 2 inputs, I had 4 rows. Now I have 3 inputs, and I have, so wait for it, 2 to the 3 or 8 rows. Okay, so each time it's going to double. So let's take a look now. These are all the possible options for these 3 inputs. Okay, and more generally, if I have n inputs, I'll have 2 to the n different rows. Okay, so to evaluate these things, we'll again take it step by step. Let's first look at each of these things inside parentheses and write them out. And you can pause the video and check if you want. Now you can combine these into the final columns, and ta-da! What do you see? Indeed, these are equal. Okay, so if I have the same truth table, again, that means these are equivalent. Okay, so we've seen a lot of examples of logical equivalences. What good is this for? Well, there's a couple different answers to this. So first of all, it's interesting, okay? Hopefully you've discovered this already. But also it allows for a lot of simplifications. For example, suppose that we're in the midst of a proof, okay? And we see at some point we've proved some statement that's logically, semantically equivalent to some other statement. Because these are equivalent, that means that I can go from one to the other. Or for example, maybe it's easier to prove one of them. As soon as I prove that statement, anything that's equivalent to that is automatically proved as well. Okay, but this goes even beyond applications of, writing proofs for fun on the weekend. There's a lot of other, maybe more direct applications of this sort of thing. Okay, so note that we have all these symbols of Boolean operators and so forth. And in a lot of different cases, the same operators are used, but possibly with different notations. For example, in Java, suppose that we're programming, we have operators for and or, and not, and XOR. Here they're denoted, for example, double ampersand and so forth. Okay? But note that a programming language itself must be formal and it must be unambiguous. Okay, and the truth tables of these things are exactly those of the logical connectives that we've seen. And everything is kind of translated over, you can use also when you're programming. Okay, so as I'll kind of close up with one specific example here. Suppose that in your code, you have some conditional. If it's the case that x greater than 0 or x less than or equal to 0 and y greater than 100, and then some additional code. What does this really mean? So translating this over mathematically, I've got A or not A and B. Take a look at the truth table of this, and you'll see something interesting. That this expression that we have written is equivalent to just A or B. So what does that mean? That means it's overkill here. This is not optimal, efficient code. I could have expressed this with a simpler condition of if x greater than 0 or y greater than 100. And this would give me exactly the same functionality. Okay, so once again, remember to go through, try to do the quiz questions on your own, and I'll see you in the next unit.